Hello, my name is Stefan, and this is homework for Physics 1 with Lab, Week 2, Demonstration of Constant Velocity Motion. This video contains 3 sections. First section is a design and setup of an experiment with analysis. Second part is the design of a mathematical model to predict the outcome of this very same experiment. And the third part is comparing the results of the experiment with the results of the model. So here we have the setup of the experiment. The moving object is a coin moving over a flat surface in the negative x direction. As a scale reference, I use this guitar, and the video clip is recorded at 24 frames per second, contains 27 frames, and goes over a total length of 1.26 seconds. Here's how it looks like. The time values are recorded here together with the x position of the coin. Now, to construct a model out of this, we need and predict the final position of the coin over here. We need to know the initial conditions, meaning we need to know the initial velocity of the coin. Initial velocity we can calculate by taking the first two x and t values. This is how it looks. So once again, here is the setup. Here's the analysis of the video. And as I said, to calculate the initial velocity of the coin, we need to take the difference in x values of the first two here over the difference of t values. That gives us this velocity vector in meters per second. So we use this to calculate, to set up the mathematical calculation model. In this model we want to predict the velocity of the coin, and we want to predict its position. To predict the velocity, we use Newton's second law here and rewrite it into this form to obtain the final velocity in a vector form. We use these values that we obtained from our experiment, and we use net force acting upon the system as 0, meaning we assume that there is no forces acting on the system, or that the forces acting on the system cancel each other out. So using these values, plugging it into this formula, we obtain the final velocity vector, and we observe that the final velocity vector is the same as the initial velocity vector. That is understandable because there are no forces acting upon the coin, and therefore the coin maintains the same velocity throughout the experiment as it moves through space. Now, to predict the position of the coin, we take its initial position and add its initial velocity times the time interval to that. The time interval we chose to be 0.01 seconds. So we obtain a final position. This is the position of the coin after 0.01 seconds. If we plug this value back into this formula, we obtain a position of the coin at 0.02 seconds. We continue to do this until we arrive at the end of the experiment of 1.126 seconds. And that should give us the final position, the very final position of the coin at the end of the table. So we take this data and plug it into the Python program. The values are set to represent the values in the experiment for the coin's initial position, velocity, mass, and down here we have the calculation. The program will calculate until 1.13 seconds. assuming a net force vector of 0, and here's Newton's second law together with the coin's position prediction formula. We run this program, get a visualization of what the model calculates, and it's a straight line, as it should be, because there's no forces acting on the coin. If we take these values, these time versus position values, and extract them and put them in a spreadsheet, in addition we'll extract these observed time and position values from the actual experiment, put them also in the spreadsheet, we obtain this. Here are the numbers in the spreadsheet, and this graph represents the data, while the orange line is the model and the blue dot are the positions in the actual experiment. Now looking at this data, we see that the model matches the observations pretty closely in the first half of the experiment. But the observations start to deviate from the model in the second half of the experiment. The reason for this is either that mistakes have been made making the observation, and the observations aren't correct, or the model doesn't fit, meaning we need to refine the model. And since factors for this could be friction of the coin to the surface, or drag between the coin and the air it passes through, or there's a slope in the table that I've used, and the coin was accelerating here, becoming faster than the model. So we need to refine this model to get a more accurate prediction. Thank you.